back to yet another video on optics, and today we are going to discuss in details about interference and the phenomenon of diffraction that we discussed last video. And you guys saw the wonderful animation made by a wonderful creator on the double slit diffraction. And we also talked a bit about constructive and destructive interference and the principle that was developed by Huygens and Fresnel. Right, so in this video, we'll be discussing in details about the single slit experiment, like the single slit interference or the single slit diffraction. And we'll also be giving some insights on the double slit interference again, or the double slit diffraction. And just to recap everything that we learned from last time, well, not everything, but the part which is very important for this video is the fact of interference. So we found out that if two waves, they overlap on each other at the same phase, they give an increased amplitude, almost, not always, but almost always double the amplitude. And if they're off phase, and in this example it is completely opposite, then they give way to destructive interference, which is in turn basically total deletion of an amplitude. Right, so we have this in mind regarding the constructive and destructive interference. And today I also tried out making some animations with Manim, a very nice animation package in Python that was created by another YouTube creator named 3Blue1Brown, a very famous guy. And I will be trying to explain single slit experiment or the single slit diffraction first with it. And then, as we also already mentioned, some insights on the double slit interference. Right, so let's go and begin with the animations. So we have a single slit of finite width and a screen. The primary wave fronts are hitting the single slit and most of it is being blocked, while a bit of it is being let through, whichever is the width of the slit. And according to the Huygens-Fresnel principle, the wave fronts are propagating as secondary wave fronts because each of the points are propagating as an individual wave front, and hence forming the single slit diffraction pattern on the screen that we notice on the animation. So now we look more into the details of single slit experiment, and we have the slit and the screen from before, and we have the primary wave fronts which hit the slit. However, as we discussed before, most of the primary wave fronts are blocked by the walls, by the two walls on the two sides of the slit, and hence they are not let through, and a part of it is let through the slit. And the slit has a finite width also to be kept in mind. And according now to the Huygens-Fresnel principle, we see that each point of a wavefront has a capacity to be a source of a secondary wavefront. So we consider each and every point of the wavefront that gets to pass through the slit, and we consider that they produce secondary wavefronts. So now they do so, and we notice why the average wavefront after the slit was not planar anymore, because it was being bent at the sides in kind of an apparent sense. So we see now the two waves coming from the two sides of the slit, like the two ends. And we see why it was not planar anymore after the slit. Now, when we take every possible angle into account, we see that we have a kind of interference pattern on the screen, and it has high central intensity while it gets weaker and weaker on the sides. We can also plot this on a two-dimensional pattern, and then we see that the central width of the maximum is really high, and then we have some very minor maximum on the ends. Consider light coming from different parts of the same slit, According to Huygens' principle, every part of the wavefront in the slit emits secondary wavefronts. These can be considered like rays that start out in phase and head in all directions. The first situation would be where the rays are parallel to each other and it would create a maximum as verified by experiments. Now, however, if we consider if the screen is placed very far away compared with the size of the slit, rays heading towards a common destination are nearly parallel in the last case. But if they go at an angle, let's say theta, whereby the phase difference between the two ends, the secondary wavefronts of the two ends is lambda, which is one wavelength, then it leads to destructive interference. We can find the pattern when we now see a next example whereby the angle deviates to 3 seconds or 3 halves, or you can say 3 divided by 2 times lambda, the wavelength, and there we get a maximum again. So basically a constructive interference. And then again, if we change it by another half of the wavelength, which is basically an angle of 2 lambda, which is 2 times the wavelength, then the phase difference between the two ends is 2 lambda. And then we get another destructive interference. So this is a pattern that has to be kept in mind for the derivation that we are going to. So if we come back to the tablet again, we saw that in the pattern that we noticed in the animations, that for the constructive interference, we always need a phase difference whereby it is always 2k minus 1 times half of the wavelength, whereby k is like a unit that belongs to the set of integers. So basically an integer. And hence it gives a maximum whereby a phase difference of basically integral number of wavelength gives you a destructive interference, and it creates a minimum. You can go back to the video and see again what I mean. There were really 4 cases, 2 being of constructive and 2 being of destructive. So we keep now this pattern in our mind, and we go to analyze the single-slit interference or the single-slit diffraction. And here I have tried to chalk up a very good diagram, although my drawing skills are becoming very rusty these days. You can very well notice it with the interference pattern that I've drawn here. It isn't perfect, I must say, but it serves a purpose, I hope. So we basically have these wavefronts, these planar wavefronts, as we also saw in the video, in the animation, and it hits a slit, a single slit of a finite width of d. Now, as we also mentioned in the video, it can go in different directions, right? And if we now consider those wavefronts as rays, basically the normal to the areas, we will again be talking about this in detail in another video, why we can do it. But here, let's just consider that the directions of the wavefronts are given by these rays here. And we can see that if it comes at an angle alpha, then we may get a constructive or a destructive interference, and thereby getting either a maxima or a minima somewhere. And we considered also in the animation, and we will also be considering it here, the primary points are the difference between the phase difference basically between the two ends of the slit. And we see that the phase difference is characterized by how far away this wavefront has gone to give in the to emit basically in the same phase in that direction, and that is characterized by a times sine alpha. I just miswrote here. This shouldn't be a. This should actually be d. So d times sine alpha, and there we go. And with a bit of geometry, we can also say that this angle alpha can also be this angle alpha, whereby this line basically signifies the line that goes till the central bright fringe, or the central bright maximum that we saw also in the video. And let's say also the distance between the slit as well as the screen, so between both of them, is E. So now we can basically chalk up a good derivation for the same. So let us first consider that we only take destructive interference or destructive, basically creating a minimum, and we are doing it because it's basically easier. We can also do the same for a maximum, but then the derivation becomes a bit lengthier and more complicated to visualize, I would suppose. So basically, if we say that the distance from the central fringe to this maximum is dk, basically k standing for the kth minimum or the kth maximum, then we can say, like, if we now take only minimum, I'll also write it down here so that it stays. And then we see that the sine of alpha is basically k lambda divided by d. So we see here that the angle alpha, sine of it is basically the perpendicular divided by the hypotenuse, and the perpendicular is basically here the phase difference, and divided by the hypotenuse, which is basically the slit width. And the tan of alpha also, which we keep as this, the tan of alpha, which we take as this one. So basically the perpendicular divided by the base, and the perpendicular here in this case is dk, and the base in this case is e. So we have this. And now if we see from the sine of it, we can actually make this as alpha is equal to sine inverse k lambda divided by d. Or we can also write alpha, coming from here from the tan, alpha is equal to tan inverse of dk divided by e. In either case, we can put one of these alphas in the other equation and get a very nice equation for the same. I will, in this case, do it for the alpha of this being placed in the sine. So I have a sine of tan inverse dk divided by e is equal to k lambda divided by d. And here you have a very nice relationship, which we can keep in mind for the single-slit diffraction. And now we'll be moving on to see how the double-slit diffraction works. However, we will not be going into any kind of derivation here. In the case of double-slit experiment, we also have two slits and a screen, whereby the wavefronts, the primary wavefronts, they should be going and being blocked at the slits. And it is basically the same case. We have again single points in each slit which create their own secondary wavefronts, and that is visualized here. And they produce constructive or destructive interference depending on whichever phase they meet, and they create an interference pattern that looks something like this. And in 3 dimensions, it's a bit more complicated. However, one does have to realize that because of the finite width of the slits, the interference pattern of the double slit diffraction, when the wavefronts hit the slit, is modulated by that of the single slit at each slit individually. So the pattern that we see on the screen for a double slit diffraction is modulated by that of a single slit. If you liked the video, please press on like, and please subscribe to the channel if you want more of such videos coming. Until then, stay good, stay healthy, and we meet again at the next video. Bye bye.